Unit 2, essay question number 2. So smooth muscle comes in two different forms. So the first is phasic, and the second is tonic. So we'll start with the phasic smooth muscle. We'll draw it out in a diagram of how it functions, similar to how we did skeletal muscle. So we'll draw the little nebulin chain with actin all over it, and we'll draw the myosin head here with ADP and the inorganic phosphate in the cocked position, not yet attached to the actin. So in this first step coming down here, we will have three things occur. So calcium will enter the cell. We'll have MLCK, which is a myosin light chain kinase. MLCK will enter. And we'll also at this point have another ATP. I'm actually going to circle this ATP in blue so we can keep track of where that goes. In this second step now, the myosin head has attached to the actin. It still is ADP, and it is still in the cocked position with the phosphate here, but now there is another phosphate here. And that phosphate, this phosphate, came from this ATP. And I'll explain the purpose of the MLCK and its functionality in a second, and that will show how the ATP, the phosphate came off of that ATP. So here in this next step, this is spot 2, we'll have that same power stroke as before, where we will have a phosphate come off, and in this case it's this black phosphate that will come off, and the ADP will come off of the myosin head. So at this point we are looking like this. So now it is uncocked, and so it's in this position, just a myosin head, but this phosphate is still here. And let me draw this actually just a little bit better. It is not attached, so let me draw it kind of down here. There's still a space right here. At this point, so this is at 3. Oh. Put that back on the black, and back on 3. It will now come up here, and that ATP is actually going to come back, and we'll have this blown up right here, another actin chain, and it's going to remain uncocked because it is no longer moving there. So we'll throw this ATP back on the myosin head, and this phosphate still is there and has not gone anywhere. Now in this last step, there's two options. You can hydrolyze, and it will skip that first step, and it will come here. So this is hydrolysis, where it will rebind. Or you can follow it back to the top again, where another molecule called MLCP this time will come in, and it will remove this blue phosphate that we've drawn. And the whole thing can start over if it follows that last pathway instead of hydrolyzing and skipping straight back to step number 2. But now we have the tonic smooth muscle. So we'll set it up the same way, this drawing. the actin here, a cocked myosin head with ADP, zoom that in a little bit, and a phosphate attached. So we have a couple of these same steps occur here. We'll have calcium, that's where it always starts, with calcium, muscle contraction. We have MLCK, and we will have an ATP again. So the exact same start. And then this is where we start to differ just a little bit. So we attach the ADP myosin head in the cocked position. We have a phosphate here, a phosphate here, again, like normal. Now, in this third step, or it's the second step, excuse me, we're going to have the first phosphate fall off, gone, and then at this point, MLCP will knock off the other phosphate. And so we have an uncocked myosin head attached to the actin, at which point we will add on an ATP, and this will remain uncocked. We have an ATP on there, and it remains in this state called a latch phase. And this is considered an indefinite stage. This is where we could have really anything happen. This is a smooth muscle where you have a sphincter involved, where you will go through this. You'll go through this process here, and when you reach this latch phase, you can hold your sphincter for hours and hours and hours. I think at this point it would be helpful to talk about MLCK and MLCP. So MLCK, let's see if we can draw this. This is MLCK inactive. This is what it looks like when it is not being activated for use. And then when it is active, it just opens up. And when it opens up, it is because of something called calmodulin. Calmodulin is kind of a miniature looking MLCK, except it has some binding sites on here that have a high affinity for calcium. So calcium will make this attach here, which activates MLCK. MLCK will take a molecule of ATP and run it through its mouth here and snip off one of those phosphates. So it will make it an ADP plus that inorganic phosphate. And that's important for this step here. When we add that ATP, because the MLCK was added first, we add only this phosphate here. And that's helpful to keep this phosphate to take it through a hydrolysis quickly if need be for a phasic muscle contraction, which would be things like your intestines when they're going through peristalsis. But now we'll talk about the MLCP and how that works, because it is slightly different. So MLCP it's like this little circle. This is a slit that opens. It has a phosphate attached here. Excuse me. So this is the inactive version of MLCP, yes. So MLCP is dependent on another molecule called Rho kinase. When Rho kinase is active, with the use of an ATP molecule, it will go and snip off that phosphate group. And so when MLCP is activated, you will have this open. So this is active MLCP. So this phosphate here is gone. There's no more phosphate. And that is because Rho kinase, which is, we'll call this square, Rho kinase, has been inactivated, no longer in use. And that is because of a high volume of sustained calcium in the ICF. Because of that, we are able to keep this open, the MLCP open, which is important here for going and taking off that final MLCP here for that final phosphate, for it to return to its cocked, unbound position next to the actin. And by having these two things, they are useful for, here, we can go back and actually name these really quick. So these are useful, phasic is useful in like the large intestine for things like I said, peristalsis, to move things through, that will keep that going. And this is good for sphincters, the sphincter, and keeping it in use for hours. And that's why this latch phase here is important, because it doesn't just release. You can hold on to that position for a long time. And that's why it still is attached here, in that position, in the uncocked position. They are all similar to skeletal muscle because of this right here, calcium. And the first step in the cross-bridge cycling of skeletal muscle is the use of calcium every single time. The other ways that they are similar and they're different is when they function. And I've mentioned this already a few times, but the function of skeletal muscle is to contract and be used immediately, depending on the type of muscle, fast or slow twitch, but it's for use in the moment. Peristalsis can happen in the background. It's something that is an automated movement, and so is the tonic, until we can take that one over and choose to move it if we need to at certain sphincters. But the skeletal muscle is totally up to us to move. We think about it and we choose to move those things. The regulation, like I said, is all done through calcium. It starts with calcium, it ends with calcium. We have to use calcium to contract any type of muscle, smooth or skeletal, and that will end